here. Last time we built up a model based on the very simple conservation of energy laws, and it is, thank you very much. Part of the model was to account for the decay heat generation after we shut down the fission chain reaction. We suggested that the fission products continue producing heat, and we took a certain amount of heat for that process. And today what we try to do is backtrack now and try to learn more about that decay heat generation. It's also called afterheat, and it comes from an analysis of what are the radioactive isotopes that generate that heat even after we shut down the chain reaction and all the control rods are inserted into a nuclear reactor core. The lack of knowledge about that decay heat generation caused the unfortunate situation in the 3 Mile Island accident, as well as the Chernobyl accident, in that the operators did not understand fully the implication of that decay heat generation. So today we try to emphasize that point here. It won't let me share the screen. No, here we are sharing it. And let's make sure that we are recording. Is it recording here? Use participant chat, and anyways, seems to be doing fine. So we go to our website here and look for the chapter that will expand on the material that we covered last time. In that case, the topic is the source term. And the source term describes the heat generation even after we shut down the fission reaction. You'll find that it is substantial in the sense that it can be initially 8% at 1 second after shutdown, but then it decays very rapidly. So if you are able to cool your reactor for maybe 24 hours or 48 hours, then you are safe. If you are unable, the heat generation is so high that it can melt or it can even vaporize a nuclear reactor core. So the source term designates the radioactive releases from reactor accidents. They include 2 groups that we are going to identify. Some radioactive isotopes are short-lived. They have a short half-life, and some radioactive isotopes have a long half-life. And each one of them has some concern for us from the perspective of protecting the public as well as the operators, the people who operate nuclear power plants. So each group has different health hazard characteristics, and we want to understand what they are. You'll find that these isotopes have different effective half-lives, and the effective half-life is going to be defined as a combination of the physical half-life, like tritium, for instance, has a half-life of 12.34 years, but it has a very short biological half-life. The effective half-life is a combination of the physical half-life and the biological half-life. So what is that biological half-life? It is that if you absorb tritium in your body, the hydrogen is eliminated very quickly from the human body. That is not the same for the strontium isotope, which is efficient products in reactor accidents or in nuclear explosions, in fact, too. You'll find that the biological half-life also is very short for the cesium-137, one of the fission products that is released in reactor accidents. Why? Cesium-137, as we'll see in the periodic table of the element, is in the same column as potassium. So it has the same physical or chemical characteristics as potassium. The body does not keep potassium for a long time. It's eliminated by our kidneys in that case. So we want to analyze what are the different hazards that we have in those radioactive elements, and what is the heat generation that we get from those fission products in a reactor accidents. So once injected in the body, we'll start looking first at the long-lived isotopes. They can remain over a lifetime. So if you don't want to have isotopes that would be radioactive in the human body for all your life until you die. And however, you'll find that their activity is much lower compared to the short-lived isotopes. Sorry, they're long. If you have a long half-life isotope, its activity is going to be very small compared to the short half-life isotopes. The reason is the definition of the activity. So we define the activity as the rate of emission of the radioactivity itself. That's dN by dt. And dN by dt is equal to minus lambda n of t. Lambda is the decay constant of the isotope. N of t is the number of the atoms of isotopes emitting radiation. Now that number is negative here because it's decaying, it's decreasing in the number of radiation isotopes emitting radiation. So we take the modulus, or the positive value of the rate of change. We call this the rate equation. dN by dt is equal to minus lambda n of t. So the activity is defined as lambda, the decay constant, which is the natural logarithm of 2 divided into the half-life, multiplied into n of t. And you could see here, if the half-life is long, this is a long-lived isotopes, then the activity is small because we are dividing by a large number. On the other hand, for the short-lived isotopes, because the half-life is small, we are dividing by a small number here, the half-life, so you'll find that their activity is much larger. So a characteristic of the long-lived isotopes is that they have a low activity, whereas the short-lived isotopes would have a long activity. The natural logarithm of 2, if you remember, is 0.6931, and the n of t is the number of transformations per second, or you can call it decay per second. That's a typo here, that's E instead of CC. And that, or the units transformation per second is in the SI system of unit, the becquerel. So long-lived half-lives and low activity, hence low activity, they pose a health hazard from the perspective of their longevity and long residence time once they are absorbed in the human body. Some of these isotopes, of course, result from the fission of fissile isotopes. They are shown in figure 1. The most prominent of the long-lived isotopes is the isotope strontium-90, and we have to understand why is it that strontium-90 is such an important isotope. If you look in the periodic table of the element, you find that strontium is in the column in the periodic table of the element that's directly below calcium. So in that case, the strontium-90, if it's ingested in the body, it seeks our bones. And once it is in our bones, it mimics calcium. The body is fooled into thinking it is calcium. And it can remain there in the body for a long time, according to the figure that I'll show you. Its half-life is 28.74 years. The other isotope of interest is cesium-137. This one has a half-life of 30.04 years in figure 3, but we'll see in a moment that the cesium-137 mimics, in that case, in the periodic table of the element, potassium. So it's in the periodic table under potassium, in the same column as potassium, hence it behaves chemically the same way as potassium. And when we ingest potassium, potassium is needed in our body for the functioning of all our nerve system. Our heart would not beat without potassium in the body. Our muscles would not move So it's an electrolyte that contributes to the functioning of the human body, and potassium gets eliminated from the body if we get an excess of it. If you drink, actually, when you eat bananas, you are eating potassium, and it is eliminated from the human body by our kidneys. So one of them is of concern in terms of its longevity. It remains in the body for a long time, strontium 90. In fact, all of us here, each one of us has some strontium 90 from our bones from the time where they were testing nuclear weapons in the atmosphere. And that strontium 90 is a fission product, so it is still in the atmosphere settling down to Earth, and each one of us has strontium 90 that can be detected with very, very whole body kind counters, as they're called, very sensitive electronic radiation. So let us first look at what are the long half-life fission product isotopes. We mentioned strontium 90 right here, 28.74A. A stands for annum from Latin. Annum in Latin means a year, so 28.74 year, and cesium-137, 30 years half-life. Other isotopes is some of the noble gases, krypton 85. There is also strontium 89. That's a very short half-life. It decays very rapidly. Ruthenium 106, cerium 144, and barium 140. Barium 140 also has a short half-life, so it decays rapidly and disappears, turns into some other elements. After 1 year of irradiation, you'll find that the activity increases in the reactor, and it's listed here in terms of thousands of curies. Curie is another unit for the activity per megawatt thermal. It depends on how long you irradiate the fuel in the reactor. For instance, after 1 year of irradiation, you'll find that activity is 1.2 kilocuries per megawatt thermal. What is of interest is not just the amount available or the half-life, but the boiling point. So for instance, you'll find that strontium 90 has a very high boiling point. So in that case, under normal accident conditions, if you don't reach 1366 degrees Celsius, it is in the shape of a solid. Whereas krypton 85 has a very low boiling point. So at the time of a reactor accident where you can reach temperatures in thousands of degrees Celsius, all that krypton 85 is in the form of a gas. Now, what are the health physics effects? What do we worry about with those radioactive isotopes? Strontium 90, I suggested, has a health physics hazard that it is internal. It's an internal hazard to the bone and lung. It deposits itself in our bones and into our lung. Cesium-137 has an internal hazard to the whole body because it mimics the potassium. And this one is very highly volatile. The strontium 90 is moderately volatile. The ruthenium 106 also have a hazard, the highly volatile oxide, ruthenium trioxide and ruthenium 04. And these have a hazard to the internal hazard to the kidney and the gastrointestinal tract. And barium 140 has an internal hazard to the bone and lung. You'll find that we are primarily interested for the long-lived isotopes or the long half-life isotopes. Our interest concentrates on strontium 90 as well as on cesium 137, and we'll come back to it in more detail. All right, cesium 167, thorium 139. This graph shows us the decay of the radioactivity N of T divided into N sub 0 in the radioactive decay chain. You'll find that cesium 137 decays less rapidly than strontium 90. And after 1 year, probably you are have only 20% of that's 100 years here. Only 0.2% is still there in the human body, except that, as we'll see, strontium is not removed by biological processes from the human body. So if it's in the body, it's there for a lifetime. This is what we call the decay graph for strontium-90. It shows us that here it has a 28.74 years half-life, and 100% of the strontium-90 emits an electron. So that is 100% decay of an electron. As the strontium-90 decays by emitting a negative electron, it turns into yttrium-90. And you can also read that the energy of the beta particle in that case is 0.54 million electron volts, quite significant in that case. Notice that there are no gamma rays emissions from strontium-90. So if it is absorbed in the body, it only emits negative electrons. However, if you go to yttrium-90, the daughter of strontium-90, this one starts emitting gamma radiation. An interesting aspect of strontium-90 is that the Russians, not the United States, used it as a source of energy for radioactive sources that produce electricity. You use thermoelectricity or thermionics to turn that energy from the beta particles into electricity. So they used it for their probes sent into space, whereas the United States used plutonium-238. The Russians thought that, oh, okay, strontium-90 emit only pure beta particles, it doesn't emit gamma rays, but what they ignored is that yttrium-90 that comes as a decay product of strontium-90 is itself a gamma emitter. And there were accidents in which they had some boys out in remote locations in Siberia, for instance, producing electricity for aviation buoys, like to signal locations for planes and so on. And they forgot that they were there left in the wild. Hunters and people in the wild noticed those sources of radiation, and they were warm. Obviously, they are producing heat from the decay. They come and sat next to them, and as I sat next to the sources of strontium-90, they got large doses of radiation, and there have been an international effort to collect those strontium-90 sources. The cesium-137 is the other isotope of interest to us. It is long-lived. Remember the comparison again, the strontium-90 has a 28.74 years half-life, whereas cesium-137 has a 30-year half-life. Now, this is the, in that case, it emits beta particles here, here and here. One of them has an intensity, or the percentage is 5.6%, decays into a beta particle to the ground state of the isotope of barium, barium-137. But 94% of the time, you'll find that it decays into the excited state of barium-137. And then here, you could see it emits a gamma photon that has an energy of 0.6617 million electron volts. And another photon that is 0.2835 million electron volts. So cesium-137 emits gamma rays, and this is significant energy of the gamma rays. Another use, it's not a use, but cesium-137 is used as a source for irradiating medical products, sterilization of, say, disposable syringes and medical products in general through the use of the gamma radiation that's very powerful right here. However, we'll see again that cesium-137 mimics potassium. So if it's absorbed in the body, it is not the physical half-life, the 30 years that we worry about. We worry about its effective half-life, which is a combination of the physical half-life, 30 years, and its biological half-life, which is much shorter. Before we consider that, we go to the other category of fission products that can be released in a reactor accident, and this would be the short half-life isotopes. Now, why do we worry about the short half-life isotopes? Because in the equation that we wrote earlier for the activity here, you find that the half-life is the decay constant is a natural logarithm of 2 divided into the half-life. So if you have a small number here in the denominator, the activity becomes very large. All right, so the long-life isotopes have a low activity, so we don't worry about them as much as we worry about the short-lived isotopes because they would have a very high activity. In that case, we worry about the dose rates. And the dose rate would be the activity multiplied into the energy that is released per emission of radiation divided into the mass of the tissue affected. So it becomes energy deposited per unit mass of the tissue that is affected, whether it went into, say, the kidneys or the bones, multiplied into the radiation's quality factor. Different types of radiation affect organs in the body in a different way. X-rays, for instance, would have a quality factor of 1, whereas if you have high mass ions or even high energy neutrons, that quality factor can be 20. So we account in that case for the dose rate here. We account for the types of radiation. A gamma would be the fraction of the energy deposited in the considered tissue, whether it's muscle, the heart, kidneys, the liver, or other organs in general. If you write the expression for the activity here as the modulus of dN by dt, dN by dt is equal to minus lambda n of t. So we eliminate the negative sign here, and we have an expression now, Q, the Q value, gamma, the fraction deposit in the material or the tissue, the mass of the tissue, M, the average energy of the radiation. And if you check the units, you'll find that it is units of ergs. That's unit of the energy of the radiation itself, that E average here, per gram per second. We can convert that into rem per second if you divide into 100, or you can convert it into sievert per second for the dose per, because the erg per gram is the unit of the rem, radiation equivalent man, and the sievert, 1 centisievert, 100 of a sievert is equal to 100. 1 sievert is 100 rem, so 1 centisievert or 100th of a sievert is equal to a rem. So all these 3 units here are equivalent to each other. The isotopes that have that short half-life, and we worry about them because they have now, see the half-life in the denominator. If it is very small number, in the seconds maybe, then you find that the activity or the emission rate of radiation here, or the dose rate, is going to be quite large. And what we worry about is the isotopes of iodine. One of the radioactive isotopes released, and that's what you see first in the reactor accident. In the Fukushima, the first isotope that they could measure coming to the United States across the ocean, across the whole Pacific Ocean, was a tellurium-132 isotope. So they detected it. And that tellurium-132 now emits a negative electron. It emits an anti-neutrino with a negative electron and a gamma photon, and turns into iodine-132. So it really starts as tellurium-132, but it ends up with iodine-132. And you find that that iodine-132 has a health hazard, in that the human body likes to concentrate the iodine isotope, if it's ingested or simply breathed through our lungs, into the thyroid gland. We mentioned that last time. The thyroid gland is a small gland here in the shape of a butterfly in our neck. Now, the iodine-132, as we'll see, emits radiation. And as it emits radiation, it can cause what we call the thyroid nodules, which are little cancers in the thyroid. The fascinating thing about that iodine-132 is that some people can get those thyroid nodules from just the heat in a room without being exposed to radiation whatsoever. And to cure them, Oh, you give them a dose of radioactive iodine again that goes into the thyroid and then kills those thyroid nodules. I mentioned the senior President Bush and his wife, Barbara Bush. Both of them had what's called Graves' disease. Graves' disease is a situation where the thyroid gland develops those cancers, radiation nodules, and they were treated for it with radioactive iodine. This is a schizophrenic here, fascinating topic. And they lived 20 years when they were cured of the nodules in their thyroid. So let us look at a whole list of the short half-life fission product isotopes listed here. The one that we worried about is the iodine isotope. There are quite a few of them, not just the iodine 132. 131 has a short half-life, 8 days. 132 has a short half-life, also 22.3 hours. Notice none of these isotopes have half-life in the range of the years. If you go back to the table for the strontium and the cesium, let's do that. You find that the half-life of strontium-90 is 28 annum in Latin years, and cesium-137 is 30 years. Here we are talking about very short half-lives in the minutes and the seconds in that case. So hence, the activity is going to be quite large. And iodine, as we know, at room temperature is a liquid. Actually, you can go to a pharmacy and buy a small bottle of iodine. Sometimes it's a good way of disinfecting a wound. So at room temperature is a liquid, but at the temperature of reactor accidents, it becomes a gas. So iodine is released as a gas. It's highly volatile, and it causes an external radiation hazard, and then an internal radiation hazard for the thyroid gland, and it has very high radio toxicity, so we worry a lot about the iodine. In fact, even though we have other isotopes like bromine and krypton as a gas, as a noble gas, it does not interact chemically. Xenon does not interact chemically. And tellurium is the origin or what decays into the iodine isotope. You'll find that we measure the radiation effects for the short half-life isotopes. All of them are converted in the United States to in Europe to the equivalent iodine. In the United States, we have more computer systems, so they prefer to go and consider each one of them separately. So the bromine would have half-lives in the hours to seconds. At shutdown, the activity would be 3 kilocuries or 1,000 of curies per megawatt thermal. But 1 day after shutdown, it goes down all the way to almost 0. It has some kind of a low boiling point. So it appears in reactor accidents or the temperature definitely is above 100, 200 degrees. It becomes a gas. It is highly volatile in that case, and it gives us an external whole body radiation, a moderate health hazard. Krypton is a noble gas. It doesn't interact chemically with the human body, but you could see that it have a very low boiling point. So in any accident where there is temperature, high temperature available, it's gaseous, and it gives an external radiation, a very slight health hazard. It's the iodine that we worry about in terms of short-term isotopes releases in nuclear accident. The xenon isotopes, that's a noble gas. They don't interact chemically. So it gives, like the krypton isotopes, an external radiation and a very slight health hazard. It is highly volatile. In the case of accidents, it is in the gaseous form. And tellurium comes as a product of uranium oxidation, and it is the source, as I suggested, of the iodine isotope. And the external radiation is basically a health hazard from the daughter, which is the iodine 132 isotope, since we suggested that tellurium 132 is the first really detectable isotope from a reactor accident, but it decays into the iodine isotope in that case. I plotted the decay graph for the two isotopes of interest to us here, the iodine 131, that's N of T divided into N sub 0. And you could see here at, now the time is not in years, like in the long-term isotopes, the time here is in hours. It disappears very quickly. The iodine 133, the iodine 131 remains there for some time, 500 hours, like say, about 20 days or a month. The iodine 131 released in a reactor accent, of course, if it is inhaled in our lungs, it eventually goes to the thyroid gland. But it also deposits itself on grasses and grazing materials in the fields. Cows graze on the field like alfalfa or clover. And the iodine would end up, in that case, in the milk of cows, and people drink their milk and feed it to their children and babies. So when there is a reactor accident, and it happened in Europe and in other accidents, the wind scale accident, for instance, you'll find that they stop grazing of cows. Cows are kept indoors, are not allowed to go and graze outdoors, are fed food that has been stored in the barns. And in that case, it doesn't find its way into the milk supply system. After a month or so, then the cows are released to the environment. All that iodine would have disappeared from the environment. What does it turn into? The iodine 131 has a 0.97, actually 8 days half-life. It emits lots of beta particles here, you could see. 89% of them have an excited state. They emit all those, the iodine 131 emits all those different gamma ray photons from the excited state all the way to the noble gas xenon 131. So now this one does not react chemically. So we worry primarily about the iodine 131 in the case of the long-lived isotopes in general. Okay, now we come to the very interesting aspect that is not very well covered in textbooks on reactor safety, is the effective half-life. As I suggested, some of those isotopes remain in the body because they are not eliminated by our filtering processes. Remember, we have our liver that filters any heavy elements like any lead or any cadmium. And we have our kidneys that also filter any materials that the body does not accept. We are a creature that doesn't like the heavy elements, so we have the liver and the kidneys to filter them out of our body. We suggested that cesium-137 acts like potassium. And if you drink, say, Gatorade, watch on the contents of Gatorade, it contains potassium as an electrolyte. It's recommended for people who do or exert in sports activity in the summer, because in that case, when they sweat, they lose lots of electrolytes, and potassium in particular is important for the human body. So down in Florida, the temperature is very high. They have athletes in the Florida Gators, one of the sports teams. So they invented for their players a mixture of sugar and water and potassium as electrolyte to replace the salt or the liquid that they use when they basically exert themselves in sports training and activity. And eventually they've discovered that there is a commercial value for what they were feeding their players, and it became Gatorade. Who hasn't drunk Gatorade among us? It's a liquid now, and it's a commercial product. And if you read the content of the Gatorade, you'll find that it contains that potassium as an electrolyte in that case. So the electrolyte, because potassium is eliminated from the human body by the kidneys, and also the process of sweating. When we sweat, we lose the sodium chloride, the salt in our body, we lose the potassium. So you'll find that potassium is eliminated from the body. So it is not just that it has a physical half-life, it also has a biological half-life. The body eliminates it and we get rid of it. So in that case, we define the effective half-life which is a combination of the biological half-life, T sub B here, as well as the physical half-life or the radioactive half-life. And you notice here, this is the law that combines two resistors in parallel. If you put in two resistors in series, the combination is resistance of the first resistor plus the resistance of the second resistor. If you put them in parallel, you'll find that the effective resistance is 1 over the resistance of the first element plus 1 over the resistor of the second element. And it seems that it applies to that effective half-life of basically an isotope that has both a biological half-life as well as a radioactive half-life. So in that case, we can calculate the effective radioactive and biological half-lives of typical isotopes. Let's start with, again, since we are emphasizing strontium-90 and iodine-131. We suggested that for strontium-90, it's a long-lived isotope. It's 29 years half-life. And the biological half-life is quite large, 50 years. So once the strontium-90 is in our body, you can calculate the effective half-life using that simple equation. We can modify it a little bit. Simply take the common factor here as T radioactivity multiplied in T sub B, the biological half-life. You'll find that you can add now the T sub B plus T sub R and then take the inverse. You get the effective half-life 1 over TF. And it's really the product of the radioactive half-life into the biological half-life divided into the sum of the two half-lives. You can check the numbers I have in the table here. But for strontium-90, if you take the biological the physical half-life plus the add to it the biological half-life, you get an effective half-life of 12 annums, stands for years. The critical organ in that case, you have to remember this if you are going to do any work in radioactivity, nuclear medicine, or in the safety field in general. It is a fission product, but the critical organ is the bone. So if it's in the bone, because the body replenishes somehow our bones, and if you don't get enough calcium in your body, your bones will become brittle over time. And we get calcium from vegetables like lettuce, for instance, and we get it also obviously from milk. You know that your parents would have recommended that you drink milk so that you can get the calcium. The iodine-131 is very interesting, though. It has a radioactive half-life of 8 days, and the biological half-life is 138 days. When we apply the combination formula for the effective half-life, you find that it tends to be the smaller value, close to the 8 days. So within 7.6 days, that is the effective half-life. You need to remember that the critical organ is a thyroid gland. It is also a fission product like the strontium-90. One way of protecting against iodine-131 affecting the thyroid gland is in the case of a nuclear accident, or like already in Europe, they are fearing a nuclear war. So they're passing around to their citizens in the Balkan states, like Lithuania and Latvia. They're passing around pills that contain sodium iodide, potassium iodide, sorry. Those pills are given to people supposedly if there is a nuclear war there and they are exposed to radiation. The potassium iodide would go and saturate the thyroid gland, and supposedly if the thyroid gland is saturated with iodide or potassium iodide, to be more exact, then in that case, any radioactive iodine-131 does not go to the thyroid gland. So this is the threat of nuclear war. If you go to a site like called the defcon.com, you'll find that Europe is in a DEFCON state right now of 2. And in the United States, they're trying not to have people panic. We are in a DEFCON state of 3 if you follow the media, and we are under a threat of nuclear war. DEFCON stands for Defense Readiness Condition. And when it is 1, this means, oh, we have a nuclear war on our hands. In the United States, again, we are close to 3. We should be 5, not 3. And Europe is at a state of 2. All right, other elements that we can calculate the biological half-life for is tritium. Tritium is very interesting. It's an isotope of hydrogen. It has 12 years of a half-life. The biological half-life is 12 years. If you take the combination of them, you end up with almost 12 back again, about 11.97 half-life. Tritium is an interesting isotope. It only emits beta particles. It doesn't emit gamma radiation, so it's very suitable for any kind of research in biological processes. It gets really lost from the human body with a very short half-life, effective half-life. Within 12 days, half the tritium, so that's injected in the body, is lost. The critical organ, hydrogen, goes to the whole body, and it comes from induced activity and fission products. It's called tertiary fission. When the uranium isotopes fission, some tritium is released, and it acts as tritiated water, meaning water where instead of H2O, it would be T2O, or TGO, or THO. Manganese 54 is another one of the short half-life isotopes. You could see it's 300 days or 1 year. The biological half-life is 25 days. If you apply the formula for the effective half-life, you find that you get closer to the short half-life, the biological half-life. So it would be eliminated from the body with a half-life, effective half-life is 23 days. Iron 55 has a biological half-life of 600 days, 2.3 years physical half-life. It gets eliminated from the body in about a year. The manganese 54, as I suggested, the liver in our human body is the filter that filters the heavy element. So in that case, it filters the manganese, and it's caused by induced radioactivity. The iron goes to the spleen that eliminates it from the body. The iron 59 also goes to the spleen, 41 or 42 days half-life. Cobalt 60 is a nasty one because it goes to the whole body, and it's a very powerful gamma emitter. Still, it is eliminated from the body because it's a heavy element, and its half-life is 5.5 years. Its biological half-life is 99.5 years. How do we determine the half-life, the biological half-life? Basically, scientists carried out experiments on mice and monkeys and dogs and animals in general. The mice behave somehow like humans in a way, and they determined the half-life in that case. So cobalt 60 is a powerful gamma emitter, and it's a whole body. What's induced activity? It's when materials in the reactor structure, cobalt 60 would be the iron, for instance, in the spacers, or the iron in the pre-stressed concrete. In the cobalt is an alloying element for iron alloys in general. So the main concern that we have definitely is strontium 90, iodine 131. We need to remember that strontium 90 has a critical organ in the bones. The iodine 131 has a critical organ in the thyroid. Cesium 137, as we suggested earlier, is for the whole body. And notice again, because I told you that we have those elimination processes, the cesium 137 has a physical half-life of 30 years. A stands for annum, but cesium 137, because it acts like potassium, is eliminated by the kidneys with a biological half-life of 70 days. So if it is ingested in the body, it doesn't remain really those 30 years, the same as strontium 90. it remains only with an effective half-life closer to the biological half-life, 70 days only. Plutonium-239 would be a very nasty one. It has a physical half-life of 24,110 years, depending on whether it goes to the bone or the lung. A biological half-life is 200 years and 500 days here. So if it goes to the lung, it's eliminated with a half-life of 500 days, 2 years. But if it goes to the bone, the same as the strontium-90, it is there for a lifetime, 198 years half-life. All right, so this is basically what we have to worry about. I show you here a procedure to show how to generate a decay curve, and I'm showing it here for the isotope, let me see, of tritium. You could see that tritium here decays quite rapidly. It has a half-life of 12.34 years. So at 12.3 here, if this is 10, let's say that's 20, like 12.3, you go up here and you find that you are at 0.5, meaning you lose half of it within 12.34 years, a half-life. And if you produce tritium for biological applications experiments, within 1 year only, you'll find that it decreases by about 5%. And as you know, tritium is used in biological weapons, in thermonuclear weapons. So they have to produce tritium continuously to provide the DT reaction that is important for thermonuclear weapons. But tritium has lots of interesting applications. All LCD kind of systems, like the screen here that I have on my computer, the watch that I have on my hand, the screen on our phone, have tiny amounts of tritium produced by the Canadians in their CANDU reactors, where they use heavy water, G2O, and the neutron is absorbed into deuterium, it produces tritium. Tritium is used in all these electronic devices for activating the phosphors that gives us the color in LCD displays. LCD displays also are used in that sign, the exit sign. So if you don't have electricity, it will be totally dark. And the exit sign uses that kind of an isotope to show us how to exit the building in the case, say, of a hurricane or a tornado in our case, or a fire in general. All right, so in that case, we know what is the source term, what is radioactivity that we should worry about in the case of a reactor accident. And the next step is to go and see how this radioactivity in that case leads to the decay heat generation that caused our 3 major accidents, the Chernobyl, 3 Mile Island, and the Fukushima accident. And then we'll try to make the case that we need to switch from solid fuels in nuclear reactors into liquid fuels. If we use a liquid fuel like a molten salt, you can continuously eliminate those fission products, radioactivity. And we'll leave this for next time. And thank you for your attention this afternoon. I hope you all survived the storm that is bothering all of us right now. Thank you.